we saw in the previous case, right, when we brought the what was that vendor for the CPU, right? That became a categorical variable or a discrete variable. It becomes very clumsy to deal with when you're talking about a linear classifier. So what we do is we use a different approach which is known as logistic regression. The idea is that we will consider a binary dependent variable in these cases, which is basically considered either 0, 1 or yes, no. Because even if there are multiple other outputs, say 1, 2, 3, 4, you can always, refactor it as a binary problem. And binary logistic regression model is used to whether what is the influence of each independent variable on the outcome, which is a discrete. And here, instead of having a notion of a equation like y equal to x mx1 m1x1 plus m2x2 plus m3x3, we will use a notion what we used in Bayesian reasoning. We said that if you had an event, the probability of that event was dependent upon conditional probability of A given C1, sorry, x1, x2, x3, x4, right? That was dependent upon probability of x1 multiplied by probability given A given x2 if they were identically distributed and independent. So we will basically use a probabilistic approach to determine the influence of an input variable on the dependent variable and sandbox the output to somewhere between 0 and 1. So that is why we say that instead of predicting whether it's going to be yes or no, we indicate the probability with which it is going to be yes or no. In linear regression, as I saw, right, we were talking about a linear function for the output y1 equal to m1x2 plus m3x3 plus m4x4, etc. In the logistic regression, we estimate the probabilities by looking at what is the potential influence on the probability of the occurrence of the target and take an approach by individual coefficients in this format. And there is some amount of mathematics involved, but key you got to understand is the transform we use is something known as logic transform. Logic transform effectively transforms your data to obtain between 0 and 1. So what we need to do is we have to now determine what is the maximum likelihood of the potential class given the data set, and that is where you have to identify the weights for each of these variables, and we will try to maximize the likelihood of the particular output given the input values. So that is what is the criteria in logistic regression, where instead of identifying the coefficients of variables which will form part of the straight line which will describe your model, here the weights will describe relative influence of the variable in maximizing the probability of that event occurring. So in logistic regression, as we saw in yesterday's Bayesian example, we will typically measure the effectiveness by means of the confusion matrix. We saw yesterday, right? While we were talking about creating a way by which you measure the effectiveness of the learned model, you try to look at what are the ones which are tested false positive or which are the ones which are tested basically true negative. The idea is that we need to understand that those which are not along the diagonal are the ones which are the misclassified instances. That gives you a measure of the effectiveness of your regression model. So let's go to the tool. I don't, because there's a whole bunch of mathematics which describe what logic means. It basically is the way by which you can transform your data to come arrive at between 0 and 1. But let's, for a moment, you think of it as 1:1 correspondence between linear regression. The efficients are about identifying way by which you reduce your error. In logistic, it's about identifying the coefficients which influence the maximum likelihood of a certain class to occur. So that is what you find out, what is that logic function, which is going to be the plot. The ultimate plot is going to look something like this, depending on your W's. So let's go to Veka. So there is a file called diabetes. You open the diabetes dataset. So what diabetes, if you look at the class variable, it is very clearly a discrete variable or categorical variable, because it is not having a continuous split. Some of these variables are discrete, some of these variables are, actually all of them are probably continuous. Okay, so now this is a perfect example where we have to run our logistic regression. Go to classify, go to choose, you say, I will say simple logistic, sorry, I'll say logistic, then I'll say I will run. So what we found is ultimately there is a good number of misclassified instances in the top 60, 115 out of the total, I think 768 odd. Let's go up a little bit. So you see the coefficients here for variable pregnancy, it says minus, for tested negative, it is minus 0.1232. For plasma, it is minus 0.032. So let us look at the semantics of it. What does tested negative for diabetes means? It means there is reduced probability of diabetes, right? Now let us look at a variable like, are you pregnant? Something related to pregnancy. It's definitely a positive indicator for diabetes. So if you want to take the negation of diabetes, it will be a negative influence, right? Same way, if your mass is higher, means weight is higher. I'm sure as your weight is high, you have a different influence. In fact, probably you have a very reasonably high influence on. But let's take the insulin. This is interesting. If you're taking insulin, it is a very definite positive indicator of reducing diabetes, right? So that is where you are getting a positive influence here, saying that this has reduced your diabetes. So that gives some kind of an indication. But at the same time, it is not I would say, very perfect fit because there's reasonable number of misclassified instances. Let's try with percentage split, maybe 90% split. Yeah, I think this is going much better. Sorry. Let's take 80% split. Yeah, so I think if you do based on a test and train combination, we're probably getting a better approach to because probably you're testing it on a smaller sample. So I don't think it's very different. In cross validation, you're doing it for a bigger sample, whole data. In case of random, what you call training and testing combination, you're probably doing a what do you call testing on a smaller subset. But I think you got to understand here that it is. Let's visualize it. How does it look like? Let's go class. So what you find is in case of visualization of a class variable with respect to insulin, you typically find there's major is more like tested negative, right? That's what it is giving here. It's not on the right side. The data is pointing to the left hand side, which is basically going to class variable is the output variable. So what did we see here? We saw, let's try one more example. Let's go to choose, sorry, open file. We worked with iris data, right? So let us see if we can run logistic regression on this. Yeah, logistic regression is a good way to work with the iris dataset, which is very similar to the dataset we worked with diabetes, because diabetes had discrete output variables. Even in iris, we have discrete output variables, right? So here again, we're finding that let's do cross validation, then we'll see how it looks like. So I think it's a fairly well distributed sample. So the model you generated is probably pretty good with the logistic regression. So what is the criteria for choosing the algorithm which you will do? As I said, you have to first inspect the input variable types. You have to inspect the output variable types. Then decide upon what kind of modeling will help. Is it a output variable which is continuous? Is it output variable which is discrete? Then go into a linear regression, sorry, or a logistic regression. Or in case of linear regression, you could also look at other